All right, welcome back everyone. I hope you're having a good week and I hope you're making progress on the assignment. You've got a bit less than 2 weeks to go, so make sure to get started on that. Remember, there's a lot of help you can get in the help sessions, so if you get started early, then you can more easily get help. If you start the assignment late, then the help sessions are going to be really busy, so yeah, just saying. All right, so what are we going to cover this lecture? So in the previous lecture, we talked about graph traversal, right, and the different kinds of graph traversal, BFS and DFS. In this lecture, we're going to be looking at some common or basic graph problems, and we'll apply graph traversal to solve these problems. All right, so what are the common graph problems that I'm talking about? Right, so one of these problems is there a cycle in the graph? Right, I want to know if there's a cycle. How many connected components are there in the graph? Is there a path that passes through all the vertices? And is there a path that passes through all the edges? All right, so the first problem is there a cycle in the graph? Right, so just to recap, what is a cycle? Well, a cycle is a path of length greater than 2 in an undirected graph where the starting vertex is the same as the end vertex, right? And no edge is used more than once. All right, so if we look at this graph, we can see that it has 3 distinct cycles, right? There's a cycle with 1, 2, 5. There's another cycle with 2, 5, 6. And there's another cycle with 1, 2, 6, 5. Right? And these are all distinct because they have different sets of edges. All right, so how might we check for a cycle in a graph? Right, so here's one idea. Right, so let's try and perform a DFS, right, to find if there's a cycle. So we'll perform a DFS, start at any vertex, and during the DFS, if at any point the current vertex has an edge to a vertex that we've already visited, then that means there's a cycle. Okay, so here's what the approach might look like on this graph. Right, so here's how it might behave. Suppose we start at vertex 0, right, and we perform a DFS. Right, then from 0, we're going to recurse into vertex 1. Right, then from vertex 1, we're going to recurse into vertex 2. So I'm assuming here that we're prioritizing lower numbered vertices. So from vertex 1, we would go to vertex 2. Then from vertex 2, we would go to vertex 3, but there's a dead end at vertex 3. Right, so there's no cycle there. So we would backtrack to vertex 2. Then from vertex 2, we would recurse into vertex 5. Then from vertex 5, we would recurse back to vertex 1, and we would see that there's a cycle because we've already visited 1. All right, so that's the main idea. Okay, so here's how the code for that might look like, well, the pseudocode. All right, so we have a function has cycle that takes in a graph. So first, let's pick a particular vertex in the graph, right? So vertex 0, for example. Then we need to create the visited array because that's what we need in a graph traversal, right? Initialize that to false. Then we're going to call our recursive helper function, right? That takes in a graph, the vertex that we picked, and the visited array. And what does the recursive helper function do? Well, it does something very similar to the recursive function for the DFS, or for normal DFS. So it marks a vertex as visited. Then for each neighbor of the current vertex, we check if the vertex has been visited. Right? If the vertex has been visited, then that means there's a cycle, so we return true. Otherwise, if we haven't visited that vertex before, then we would recurse into that vertex and see if we can find a cycle from that vertex. Right? So we recurse and pass it vertex W. Right? And if we can find a cycle from that vertex, then we return true. Otherwise, if we checked all our neighbors and there are no cycles from any of the vertices, then we return false. Right, so that's how the pseudocode would look like. Okay, now let's try and run this function because I have it implemented. All right, so here it is. So in this program, I just read in the graph and then print out the graph and then call the hasCycle function. It's going to check if there's a cycle and it's going to print out a message by telling us if there was a cycle. Right, so these functions are just implemented the way the pseudocode was written. So, create a visited array, call the recursive helper function starting from vertex 0, and then this is the recursive helper function. All right. So all the same, let's compile the program and see how it performs. So I have a couple of test cases in the tests directory. Right, so here is how the test cases are formatted. So the first line is just the number of vertices in the graph, and the remaining lines are just all the edges. All right, so I've got 3 different test cases for cycle. Right, and the first test case is just the graph from the slide, so this one. Right, so let's see if the graph has a cycle. So cycle check, and I'm gonna pass in this file containing the graph, right? And it says that the graph contains a cycle. All right, now I have another test case here, so let me open up that one. Okay, so here's the other test case. Now this one is the same as this graph, except it's missing a couple of edges, right? So it's missing 1, 2, and it's missing 2, 6, right? So without these edges, there shouldn't be any cycle in the graph. Right, so let's see what happens if I run this. All right, and it still says there is a cycle, right? So clearly there's a problem with our algorithm, right? So what's wrong? Well, there's a bug, right? So the problem is that the algorithm doesn't check whether the neighbor that we're going to is the vertex that we just came from, right? So for example here, when we're at 0 and we recursed into 1, right? Well, a neighbor of 1 is 0, right? So we're gonna check if 0 is being visited, and it's already being visited because that's the vertex that we started at, right? So because 0 has been visited, it thinks that there's a cycle, right? And we can see this if we add some print statements to our cycle check function. Well, let's add some print statements here to see what's going on. Right, so whenever we recurse, I'm going to print out a statement that says going from v to w, and whenever we found a cycle, I'm going to print out found cycle going from v to w. All right, so I'm going to just add those print statements. And now let's see what happens when we run it on our first graph. Okay, so actually, let me check what I did. Oh yeah, so, okay. Let me just restructure the program a little bit because it didn't print things in quite the order that I wanted. All right, so I'm going to take this line, put it before the recursive call, all right, and then do that. All right, so now it's actually going to print out going from v to w before the recursion. All right, so let's see what happens. Right, so the function goes from 0 to 1. That means it's recursing into 1. And then it says it's found a cycle going from 1 to 0. Right, so this is the cycle that it thinks it's found. Right, but this isn't a cycle, because a cycle should have, shouldn't involve the same edge twice. All right, so what is the fix? Right, so now since we're treating the previous vertex as a new vertex, and we're going back and forth along the same edge, let's keep track of the previous vertex during our DFS. All right, and when we're considering our neighbors, in order to recurse, we just ignore the vertex. All right, so here is the improved attempt. So this function here, our recursive helper function, is going to take in the current vertex, but it's also going to take in the previous vertex. Right, so v and previous. And during our loop, when we're checking for neighbors, if the neighbor is equal to the previous vertex, then we continue. Right, so continue means go back to the beginning of the loop. All right, and in our original function hasCycle, when we initially call it, we'll just pass in v twice. That's fine, because v is not going to have an edge to itself. Okay, so let's try and implement this. So we'll modify our implementation in order to add that fix. So now our function takes in a previous vertex. Right, and our hasCycle function is going to pass in the starting vertex twice, 0, 0, and our helper function is going to take in a previous vertex, and if our neighbor is equal to previous, then we continue. Okay, so that's almost it. So when we recurse, we have to pass in v as the previous vertex. Okay, so we recurse on w, we pass in v so that the function knows where we came from. All right, and now let's run the program. First, let's run the program on the first test case, which is our original graph, this one. Oh, whoops, not this one, this one. Right, so what we expect now is for the program to go from 0 to 1, then from 1 to 2, then from 2 to 3, right? But then it's going to backtrack to 2, then go to 5, and then find a cycle at 1 when going from 5 to 1. Right, so those are the print statements that we expect. All right, and that is indeed what happens, right? So we go from 0 to 1, then we go from 1 to 2, then we go from 2 to 3, but that's going to lead to a dead end. Then we go from 2 to 5, then we find a cycle going from 5 to 1, okay? So, yeah. All right, so I have a third test case here. So let's see what happens when we run it on this test case. Oh, actually, let's run it on the second test case first. So we see that the graph doesn't contain a cycle, right? The recursive function does, visit every vertex and finds that there's no cycle. I have a third test case here, which looks like this. I'm going to show the graph to you guys in a second, but this graph should have a cycle. But when we run it, it says that the graph contains a cycle. Interesting. So let's see what happened. 0104. Okay. Just need to update this real quick. All right. So this graph should have a cycle, and our program says that it doesn't. All right, so here is what the graph looks like. So the graph has multiple connected components. Right? So the problem with our algorithm is that the algorithm only checks one connected component. Right? So if we start at 0, it's only going to check this connected component, right? Because DFS only traverses, the connected components of the vertex that you start at. Right? So if we start over here, then we're not going to find the cycle over here. Okay? So how do we fix that? Well, after we finish our initial DFS, right, if any vertex hasn't been visited yet, then we just perform a DFS on that vertex, right, and just repeat until all the vertices have been visited. Right, so to fix this, it's not too hard. All we have to do is to add a loop to our initial function, right, where we check if the vertex has been visited or not. If it hasn't been visited, then we just call our recursive helper function. All right, so let's modify the program yet again. Oops, not here, but here. All right, so we're going to create a loop that starts at 0 and goes up to G and V. Right. And if the graph has a cycle starting from vertex V, then we'll free visited and return true. Oh, and also, we only want to call DFS has cycle if V hasn't been visited yet. Right. So if V hasn't been visited from a previous DFS and there is a cycle, then we return true. Otherwise, we're going to return false. All right, so now let's see whether our function works on the third test case. All right, so it finds a cycle. All right, so when did it find a cycle? Well, it started at 2 during the second DFS. All right, so here, it started at 2. Then it went to 3, which was a dead end. Then it recursed into 5, then to 6, then it found a 2. Right, so going from 2 to 3, going from 2 to 5, going from 5 to 6, then found a cycle going from 6 to 2. Okay, so that's the pseudocode, and this now works. Okay. Right, so how efficient is our implementation? Right, so this algorithm is just a slight modification of DFS, right? And we know from Monday that a full DFS traversal of the entire graph is O of V plus E, right? If we use the adjacency list representation. Right, so that means the worst case time complexity of the cycle checking algorithm is O of V plus E. All right, so that is cycle checking. Now let's talk about connected components. All right, so what is a connected component? Well, connected component is a maximally connected subgraph. So a couple of big words there. We'll go through the definitions, but I think it's pretty intuitive what a connected component is when you look at a diagram of a graph. Right, so this graph has 3 connected components, right? Because you kind of have 3 different islands, right? Where it's not possible to reach one island from another island. Right, so the definitions, so a subgraph, remember, is a subset of vertices and edges of the original graph. Right, a connected subgraph is a subgraph where there is a path between every pair of vertices in the subgraph. Right, and what does it mean for what does a maximally connected subgraph mean? So it means that there's no way to include more edges or vertices from the original graph into the subgraph such that the subgraph is still connected. Right, so if we go back here and we just take 2, 5, and 6, right? If we just take these vertices and the edges between them, that's not a connected component because it's still possible to add 3 into this connected component so that it's still connected. All right. Okay, so the problems with connected components that we want to answer are how many connected components are there, right? And are 2 vertices in the same connected component? All right, so how might we solve this problem? Well, first of all, let's compute an array which has 1 element for each vertex, which tells us which connected component each vertex is in. All right, so if we call this array component of, then component of V will contain the component number or ID of vertex V. All right, so for example, let's take this graph again. Right, we see that 0, 1, and 4 are in the same connected component. Right, that means in our array, index 0, 1, and 4 should have the same component number. Right, so we've put a 0 at index 0, 1, and 4, which means these vertices are in component 0. Right. Meanwhile, 2, 3, 5, and 6 are in a separate connected component, which means they should have a different component number. Right, so we see that index 2, 3, 5, and 6 all have a component number of 1. Right, then 7 and 8 have another component number, which is 2, right, because they're in a separate connected component to the other vertices. All right, so what we want to do is to compute this array. All right, so how do we do this? Well, we can use DFS again. Right, so let's choose a vertex. So usually we just choose vertex 0 to start at and perform DFS starting at that vertex. Okay, and during DFS, right, that DFS is going to visit all the vertices in the same connected component as where we started. Right, so what we'll do is we'll assign all of the vertices visited to component 0. Right, so we'll put a 0 at the indexes corresponding to all the vertices in that component. Right, then after that first DFS is done, right, if there are still some vertices that haven't been assigned the components, then we perform a DFS on that vertex, right, on one of those vertices. Right, then during that DFS, we assign all the vertices visited to component 1. Right, and we just repeat this until all the vertices are assigned a component number, right, and we just increase the component number each time. So next time, we assign all the vertices visited to component 2, then 3, then so on. All right, so here's what the pseudocode for that would look like. Right, we have a graph, and our output is going to be the component of array, right? So we want the function to return an array like this. Okay, so first of all, we create our component of array, right? Initialize that to -1. So -1 just means the vertex hasn't been visited and hasn't been assigned a component number. Right, then we're going to initialize the current component number, which is 0. And for each vertex in the graph, right, if that vertex hasn't been assigned a component number, right, then we perform a DFS starting at that vertex. Right, so DFS components V. And we also pass in the component number, right, because instead of just marking a vertex as visited, we'll give it the component number instead. All right, and after the DFS is done, we increase the component number by 1. Okay, and here is the recursive helper function, DFS components. Right, so it's almost identical to the recursive helper function for DFS. Right, so we set the component number of the current vertex to component number. So this is instead of marking the vertex as visited, we set the component number, and then for each neighbor, if that neighbor hasn't been assigned a component number, then we recurse into that vertex. Okay, so let's implement this. All right, so components.c. Right, so what I've done already is I've allocated a component of array. Right, and first thing we need to do is to initialize it to -1. Okay, so vertex v equals 0, v less than g and v. Component of v equals -1. Okay, now we need to initialize a component number. All right, so comp number equals 0, and then we're going to loop through all our vertices. And if vertex v hasn't been visited, so if not visited, but if component number of that vertex is -1, right, if the component number of v is -1, which means it hasn't been given a component number yet, then we're going to call our recursive helper function, so dfs components. So we pass in the graph, we pass in the current vertex, we pass in the component of array, and we also pass in the current component number. Right, and after we've finished the DFS, we're going to increment the component number by 1. All right, and that's it for this function. Now we need to write our recursive helper function, which is going to be very similar to our recursive helper function for normal DFS. So what is that going to be like? So void DFS components, and what is it taken? It takes in a graph, the current vertex, the array of component numbers, so int star components of, and the current component number. Right, and what does the function do? It marks the, well, it gives the current vertex a component number, so component of v equals comp number. Right, and now we're going to loop through all our neighbors. So this is an adjacency list representation, so we're going to say current equals g edges v. Right, then we're going to loop through this array. Sorry, not array, linked list. Right, so w is our neighbor. So what we're going to do is if w has not been given a component number, we're going to recurse on that vertex. Right, so we recurse on w. All right, and that should be it. All right, so now we'll take the function prototype. All right, and run it. So I have some test cases for components. Right, so the first test case should be the same as this graph here. So let's see what happens when we run it. Components, tests, components 1. All right, so what do we get? Well, 1, 4, 5. Okay, the graph, it seems like the graph is not exactly the same. So let me fix that. components 1. So we need to remove this edge here. Okay, now it should be the same. All right, so we can see that vertices 0, 1, and 4 are in the same connected component, right? They're assigned component number 0. Vertices 2, 3, 5, and 6 are assigned component number 1, and vertices 7 and 8 are assigned component number 2. So we get the result that we wanted. Okay, let me see what's in our second test case. Right, so in this test case, all the vertices are in the same component except for 7 and 8. All right, so let's see what happens when we run the program on this test case. Oh, never mind, they're all connected. So yeah, all the vertices are connected in this test case. I forget. All right, and then there's one more test case, which is there are no edges in the graph. Right? So if there are no edges in the graph, all the vertices should be in different connected components. Right, so let's see what happens. Oh, I already ran it. So yeah. So we see component 0, or vertex 0 is in component 0, vertex 1 is in component 1, and so on. Okay. All right, so what's the time complexity? Well, the algorithm just performs a full DFS, right, which is O of V plus E. And there's nothing really special to it. Instead of marking a vertex as visited, we're just assigning it a component number. Okay. Right now, so there's more about connected components. So suppose we frequently need to answer the following questions. Right, so how many connected components are there in the graph? Are V and W in the same connected component? And is there a path between V and W? Right, so it turns out that the last two questions are equivalent if the graph is undirected, right? Because if two vertices are in the same connected component, then there must be a path between them. Okay, so yeah, if we frequently need to answer these questions, right, we don't want to run a full components, run our components algorithm fully each time, right? Because this algorithm runs in O of V plus E time, which could be expensive. Right, so what we could do is to cache or save the components array in the graph struct, right, as well as the number of connected components. Right, so here's what our struct would look like. Right, so we have the fields that you would need for your graph representation, so matrix, adjacency list, or array of edges. Then you also have two additional fields, one which is the number of connected components, and one which is the component of array that we generated earlier. Right, and if we have this, these fields in our struct that let us keep this information, then we can answer these questions very easily. Right, so how many connected components are there? Right, we can answer that really easily because we can just return G and C. Right, that's this field here. Right, are V and W in the same connected component? We can answer that really easily because we can just check which component number V and W are in, right? And if they're the same, then that means they're in the same connected component. Right, the last one, so is there a path between V and W, can be answered in exactly the same way, right? Because if two vertices are in the same connected component, there is a path between them. So we just check if they have the same component numbers. Right, and we can also use this to optimize finding a path between two vertices, right? So if we want to know if if we want to find the path between two vertices, then before we actually, run the BFS or DFS, we can first make sure that they're in the same connected component first, right? Because if they're in different connected components, then there's no point running the traversal, right? Because we know that there's no path. Right, so if we wanted to check if there's, or check what the path is, then first run this check. All right, so that's the benefit of caching this information in our graph. Right, so what is the downside? Well, there's always a downside, so we need to maintain this information as the graph changes. Right, so if we insert an edge into the graph, then that might reduce the number of connected components, right? Because we might end up merging two connected components together, right? So in this graph, for example, suppose we added an edge between 1 and 2, right? That means because these two vertices were in different components, we're now merging the two components together, and that means we're going to have to, decrease the number of connected components, and we're going to have to change the component number for 2, 3, 5, and 6, right? We're going to have to change these to 0, right? Because they're now in the same component. All right, so we're going to have to maintain that. And also, if we remove an edge, then that might increase the number of connected components, right? So if we remove an edge, and after we remove the edge, there is no longer a path between the endpoint vertices, right? Then that increases the number of connected components. Right? So going back to this graph, suppose we remove this edge between 2 and 3. Right? If we remove that edge, then that creates a new component. Right? So yeah, first of all, we'd have to check whether there is still a path between them. And if there isn't, then we're going to have to update our array, right, to give the vertices in the new component a new number. Okay. All right, so that's it for connected components. All right, now let's look at the next problem, which is Hamiltonian path and circuit. All right, so what is a Hamiltonian path? So a Hamiltonian path is a path that includes each vertex exactly once. And a Hamiltonian circuit is a cycle that includes each vertex exactly once. All right, so here are some examples of these. So take the following graph. All right, so here is a Hamiltonian path on this graph, and here is a Hamiltonian circuit. Right, so the Hamiltonian path visits each vertex exactly once. Right, the Hamiltonian circuit, there's a cycle here that includes each vertex exactly once. Okay, so, all right, well, that sounds like a simple problem, right? So how do we actually check if a graph has a Hamiltonian path? So one idea is to do a brute force search, right? So we can use DFS to check all the possible paths in the graph, and recursive DFS is perfect for this because it allows us to do backtracking, right? And then during DFS, we'll keep track of the number of vertices that we have to visit, right, that we have left to visit, and then we stop when we have no more vertices left to visit. All right, so here is the pseudocode. Okay, so here's the initial function, so the top level function. So what it does is we create the visited array, right, because we're doing a DFS. So we create the visited array, initialize it to false. Right, and for each vertex in the graph, because we need to check each possible starting point, right? If we can find the Hamiltonian path starting from vertex V, we return true. Okay, and what are we passing in? We're passing in the graph, the starting vertex, the visited array, and the number of vertices in the graph, right? And we're going to use this to keep track of how many vertices left there are to visit. All right, and if we checked every possible starting vertex and we haven't found a Hamiltonian path, then we return false. All right, so here's our helper function with the important parts highlighted. All right, so we're performing a DFS starting at V. So what do? Well, we mark V as visited. Right, then since we visited a vertex, we reduce the number of vertices left by 1. Right, and then we check if we visited all the vertices. Right, so if the number of vertices left is 0, then we return true. Right, that means there is a Hamiltonian path. Otherwise, we're going to check all of our neighbors. So for each neighbor, W, if we haven't visited W yet, then we recurse on W and pass it the number of vertices left. Right, and if we can find a Hamiltonian path, then we return true. All right. Otherwise, so at the end, if we've checked all of our neighbors and we can't find a Hamiltonian path from any of our neighbors, then we have to set our, so we have to unvisit V, right? So I have to set visited V to false. And the reason we have to do this is because we need to check all possible paths in the graph, right? So later on, we're going to have to revisit V via a different path, and we need to make sure that V isn't marked as visited, otherwise it's not going to be visited again, right? Then we return false. Okay, so just an example for why we need to set visited V to false at the end of the function. Right, so why did we need to do this? Well, I already said that the function needs to check all possible paths, right, in the graph. So if we don't set visited V back to false, then the function won't be able to return back to V when checking another path. Right, so here's an example of a case where this would fail. So suppose we started at 0, right? Then our DFS is going to go to 1, then it's going to go to 2, then it's going to go to 4, right? Because it's favoring lower numbered vertices. Right, so 0, 1, 2, 4, that's not a Hamiltonian path, right? So it's going to return false, right? But we need to make sure to unvisit all of these vertices, right? 4, 2, 1, because when we go back to 0 and we head over to 3, right, we need to make sure that 1 isn't visited yet so that we can actually go to 1, right? So eventually we're going to find 0, 3, 1, 2, 4, right, as our Hamiltonian path. Okay, so let's implement this function. Okay, so Hamiltonian path.c. All right, so let's try and remember what our function did. Right, so first of all, we created a visited array. Right, so bool star visited equals, we can use calloc this time because we're setting everything to false. So calloc GNV size of bool. Okay, what do we do next? We need to check all possible starting vertices. Right, so for vertex V equals 0, V less than G and V. We need to call our recursive helper function. Right, so if DFS Hamiltonian path G, what did we pass in? We passed in the current of the starting vertex and the visited array, and also the number of vertices in the graph. Right? So if there is a Hamiltonian path starting from vertex V, then let's free the visited array and return true. Right? Otherwise, if we've checked all starting vertices and there is no Hamiltonian path, then we return false. All right, now let's implement our helper function. So DFS Hamiltonian path So it takes in the graph, the current vertex, the visited array, and the number of vertices left. Right, and what does it do? Well, it marks the current vertex as visited. Right, so visited v equals true. And then we decrement the number of vertices left. Right, now if there are no more vertices left to visit, that means we've visited all the vertices, then we return true. All right, and what do we do now? We will check all of our neighbors. Right, so hopefully you're noticing a pattern when we're implementing all of these functions. Right, it's pretty much all the same function really. So cur equals g edges v, and for, so we loop through all of our neighbors. W equals v, and if w hasn't been visited, then we're going to recurse on that vertex. Right, g w visited and numVertices left. And we have to check if this function returns true. Right, so if we can find the Hamiltonian path from w, then return true. Okay, and at the end of the function, remember we have to set visited v back to false, right? So that later we can come back to this vertex via a different path, right? And then return false. All right, then we gotta copy this for the function prototype. All right, let's compile it. And I have some test cases here. All right, so this test case should be the same as this graph on the left. All right, so there's an edge between 0, 1, and 0, 2. There's an edge between 1 and 2. There's an edge between 1 and 3. There's an edge between 2 and 4, and 3 and 4. Right, so it's the same graph. All right, so let's run it and see if it finds a Hamiltonian path. Oops. Test 2, 1. So the graph has a Hamiltonian path. All right, let's see what's in Hamiltonian 2. All right, so what's this graph? So, oh yeah, so it's this graph over here, right? So there's an edge between 0 and 1 and 0 and 3. There's an edge between 1 and 2 and 1 and 3 and 1 and 4, and there's an edge between 2 and 4. Okay. So let's run our program on this. There should be a Hamiltonian path, right? And it says there is. All right, so let's see the effects of not setting visited v back to false at the end of this function, because I bet you it'll not find the Hamiltonian path. Right, so it says that there's no Hamiltonian path. So we need to set visited v back to false at the end of the function. Okay, and there is one more test case for Hamiltonian. All right, so this one I think is the same as this graph, except there is an edge missing. Yeah, so this graph is the same, so this test case is the same as this graph, except this edge here is missing, right? And if this edge is missing, then there shouldn't be a Hamiltonian path, right? Because one is sort of acting as a bottleneck, right? Because if you start at 0 and you go to 1, then you want to go and visit these vertices, then you can't go back and visit 3, right? So let's see what happens when we run this test case. Right, so the graph does not have a Hamiltonian path. All right, and oh yeah, so how do we check if a graph has a Hamiltonian circuit, right? So we can use a similar approach as a Hamiltonian path, right? So we can use a DFS to check all possible paths, but we don't actually need to try all the starting vertices, right? We only need to try one, because if there is a Hamiltonian circuit, then we should be able to start at any vertex and find the circuit, right? So we just need to start at any vertex. And after we've found the Hamiltonian path, then we check if the final vertex is adjacent to the vertex that we started at. All right, so here's the pseudocode for that. It's not much different from the Hamiltonian path pseudocode. The main differences are we don't have a loop here to check every possible starting vertex because we don't need to, right? We just start at 0 and check if there's a circuit, right? And the other difference is over here, right? So if there are 0 vertices left, that means we found a Hamiltonian path. We check if the vertex that we're currently at and our starting vertex, which is 0, are adjacent to each other, right? And if they're adjacent, then that means there's a circuit. All right, and what is the time complexity of this approach? Right, well, the time complexity turns out to be O of v factorial, right? Very inefficient, right? And that's because there are at most this many paths to check. Right, so unlike our previous algorithms, which were O of v plus e, this one is O of v factorial, right? And why is it O of v factorial? Because we need to check every possible path, and it's because we set visited v back to false at the end of the function, right? Which causes v to be revisited, right? Every time we're checking a different path. All right, and there is actually no known polynomial time algorithm for this problem, right? So the Hamiltonian path problem is NP hard, and that's a term used in complexity theory. All right, so yeah, that's Hamiltonian path. So let's take a break here, and we'll come back in 10 minutes time. Right, so we'll come back at 3:10. Up again. Okay, so before the break, we were talking about Hamiltonian paths and circuits. So now let's talk about a very related concept, which is Euler paths and circuits. Okay, so what is an Euler path? Well, an Euler path is a path that includes each edge exactly once, right? So as opposed to a Hamiltonian path, which includes each vertex exactly once, and an Euler circuit is a cycle that includes each edge exactly once. Okay, so here I have two different graphs. Right, the graph on the left has an Euler path, right, 4, 2, 0, 1, 3, 0. Oh, I'm sorry. Okay, let me fix that. Okay, all right, so thanks for letting me know. So an Euler path is a path that includes each edge exactly once. An Euler circuit is a cycle that includes each edge exactly once. All right, and here I have two graphs. On the left, I have a graph that has an Euler path, right, 4, 2, 0, 1, 3, 0. On the right, I have a graph that has an Euler circuit, right? So 4, 2, 0, 1, 3, 4, right? That's a cycle that includes each edge exactly once. Okay, and an Euler circuit is an Euler path, all right? Okay, so a little bit of background on this problem. So the problem is named after Leonhard Euler, right? You might have seen him in like other math courses. And when did he come up with this problem, right? So the problem was introduced by Euler when he was trying to solve this 7 bridges of Königsberg problem, right? So you have 7 bridges, right, connecting different parts of the town, and the problem was, is there a way to cross all the bridges exactly once on a walk through the town? Right, and it turns out that this is a graph problem, right? So at the bottom here, I have more abstract representations of this scenario, right? So it's a graph problem because the vertices can be used to represent pieces of land, and the edges represent the bridges. Right, so here is what the graph would look like. Right, and notice that we have some parallel edges here, but that's fine. Right, so how do we check if a graph has an Euler path or an Euler circuit? Right, well, one possible way to do it is to brute force, right, to check all possible paths. But that's going to be really inefficient, right? It might be even more inefficient than the Hamiltonian path problem because you have to check all possible combinations of edges, right? All possible permutations of edges, right? And with Hamiltonian path, you only need to check all possible permutations of vertices, right? But for edges, you might have a lot more edges than vertices, right? So it could be very, very inefficient. But it turns out we don't need to do this, so there's no need to brute force it. We can use some theorems in order to tell us whether a graph has an Euler path or an Euler circuit much more efficiently. Okay, so here are the theorems. So a graph has an Euler path, right, if and only if exactly 0 or 2 vertices have odd degree, and all vertices with non-zero degree belong to the same connected component. All right, and we'll see what that means exactly in a bit. And how about an Euler circuit? So a graph has an Euler circuit if and only if every vertex has even degree, so every vertex, and all vertices with non-zero degree belong to the same connected component. All right, so let's just focus on the first constraint for now. So Euler path exists if exactly 0 or 2 vertices have odd degree, and Euler circuit exists if every vertex has even degree. All right, so now here are some examples of graphs, right? And let's see which one of these, or which of these have an Euler path and which of these have an Euler circuit. All right, so let's look at the first graph. All right, this is a simple one. Right, all the vertices have degree 2, right? Because each vertex has 2 neighbors. That means the graph has an Euler circuit, right? Because for there to be a circuit, you need to have, every vertex needs to have an even degree. All right, let's look at the middle graph. Oh, and of course, because the graph has an Euler circuit, that means it also has an Euler path. All right, let's look at this middle graph here. So let's look at the degrees of each vertex. Right, so the degrees of 0 and 1 are 3. Right? Each of these vertices have 3 neighbors. Now, the degree of vertex 2 and 3 is 4. Right? Each of these have 4 neighbors, and the degree of 4 is 2. Right? So that means we have 2 vertices with odd degree. Right? And because of that, we have an Euler path, right? But we don't have an Euler circuit. Right? And you can try and draw this shape without lifting a pen, and that basically tells you whether there's an Euler path or not, right? And how about this graph on the right? So in this graph, well, vertices 0 and 1 have a degree of 3. Right? Vertices 2 and 3 have a degree of 5, right? And that means we have 4 vertices with odd degree, and that means we don't have an Euler path, and we don't have an Euler circuit. All right? So now let's talk about the second constraint, right? So all vertices with non-zero degree have to belong to the same connected component. So why do we have this condition? That's because this graph, even though it's not connected, it has an Euler path, right? So this 4 isn't connected to anything, but there's still an Euler path, right? Just this is 2, 0, 1, 3, 0, right? That path, visits all the edges of the graph, and therefore the graph has an Euler path. All right, so yeah. So this theorem actually makes it really easy to check whether there is an Euler path or not. Right, so here's our function, has Euler path. Right, it takes in a graph G. So what do? Well, we need to count how many vertices have odd degree. Right, so we create a variable, number of odd degree equals 0. And for each vertex, we check its degree. Right? If V has an odd degree, then we increase the count by 1. And at the end, we check if the number of vertices with odd degree is 0 or 2, and if that second condition is met. Right? So I've called it Euler connected. Right? So the purpose of this function is to check if all the vertices in the graph with non-zero degree belong to the same connected component. Right? How do we do that? Well, it's a little tricky, but not too tricky. So hopefully I'll be able to explain it. So we first create a visited array, right? Initialize that to false, because we know that we're going to have to traverse the graph, right? And now we're going to loop through all the vertices and check their degrees, right? And as soon as we find a vertex in the graph with non-zero degree, so degree greater than 0, we perform a DFS starting at that vertex. Okay? So we just perform a DFS starting at that vertex, then we break, because we only care about the first vertex with non-zero degree. Then what we do, so that is going to mark all the vertices in the same component as V as visited, right? So what we do next is we're going to go through all the vertices again, and if there are any vertices with positive degree, so non-zero degree, where we haven't visited V, right? So where we didn't visit V during this first DFS, right? That means this condition is false, right? So that means not all the vertices with non-zero degree belong to the same connected component, so we return false. Right? Otherwise, if we've gone through all the vertices and none of them violate this condition, then we return true. Okay. So, so let's look at how it's implemented. So this dfsRec function is the same function that we went through on Monday. Right? It's just the helper function for recursive DFS. All right, so let's look at this function. So I have implemented this one already. All right, so it's a little more tricky, a little bit more code, but here is how it works. All right, so here's our has_Euler_path function, our top level function. It's going to count up the number of vertices with odd degree, right? And then we just check if it's 0 or 2, and if it's Euler connected. Okay, and here's the degree function. So it's very easy to check the degree with an adjacency list, right? You just loop through the adjacency list and count how many vertices there are in that list. Okay. Then here's the Euler connected function, right? So you create the visited array, you find a vertex with non-zero degree, and you perform a DFS starting at that vertex. Then you go through the vertices again, you make sure that all the vertices with non-zero degree have been visited. Right? If any of them haven't, then you return false. Okay, and here's the recursive helper function for DFS. Right? It's the same as on Monday. All right, so let's run this program, and I have a bunch of test cases for this one. All right, so first of all, I have these test cases. All right, so the first test case is this one, then the second test case is this one, and the third test case is this one. So these two graphs should have an Euler path, but the third graph should not. All right, so let's run the program and see if we get the expected result. So, right, this graph has an Euler path. Right, the second graph also has an Euler path, but the third graph does not have an Euler path. All right, and I believe I have one more test case. So Euler 4. All right, so this test case is to test this graph here, right? So this graph should have an Euler path, even though it's not connected. All right, so this graph does have an Euler path. Right? Notice that 4 doesn't have any edges to anything. All right, so we were up to here. All right, now how do you test if a graph has an Euler circuit, right? Similar deal, except all the vertices have to have even degree, right? So you go through all the vertices, you check their degrees, right? And if the degree of any vertex is odd, then you just return false, right? Otherwise, if you've gone through all the vertices and they all have even degree, then you just check if the graph is Euler connected, right? That's the way I'm expressing that condition from earlier. Right? All the vertices with non-zero degree belong to the same component. All right, so that is Euler paths and Euler circuits. So what's the time complexity? So what does our algorithm have to do? Well, it has to find the degree of every vertex. Right? That's going to take O of V plus E time, right? Because you're basically just looping through all the adjacency lists for every vertex. Right? In total, that's going to be O of E. The O of V is because you have to actually iterate through all the vertices. So O of V plus E. Now checking the connectivity requires a DFS. Right? We saw that, and that's going to be O of V plus E. So we established this on Monday. And therefore, the worst case time complexity of the graph of the algorithm is O of V plus E. All right, so unlike the Hamiltonian path problem, which was solved in factorial time, the Euler path problem can be solved in polynomial time. Right? So the word we use for that in complexity theory is that it's tractable. All right, so the Hamiltonian path problem we call intractable. All right, so here are some other problems just to highlight the difference between tractable, so solvable in polynomial time, and not solvable in polynomial time. And some of these can be quite surprising. Right, so here are some tractable problems. So can we find a simple path connecting two vertices in a graph? Right, we know how to do that, right, using BFS or DFS. So that's tractable. And what is the shortest such path, right? To do that, we can use a BFS, right? Now, this problem is intractable, and it might be surprising, right? What is the longest such path, right? This problem is not solvable in polynomial time, interestingly. All right, here's another example. So is there a clique in a given graph? Right, so what is a clique? So reminder, a clique is a fully connected subgraph. Right, so it's a subset of vertices of the original graph such that all the every pair of vertices in that subgraph have an edge between them. Right, and so the tractable problem is there a clique? Right? Now, what's intractable is what is the largest clique, right? So, maybe have a think about why this problem is tractable and why this problem is not. All right, the next example. So, given two colors, can we color every vertex in the graph such that no two adjacent vertices are the same color? Right, now this problem is solvable in polynomial time, right? But this problem is not, right? How about three colors, right? If you just add one more color, the problem now becomes intractable, so you can't solve this in polynomial time. So it's quite interesting. All right, and here is another problem which is not solvable in polynomial time. So graph isomorphism, right? So this is the problem of are two graphs identical if we just rename the vertices, right? So these two graphs may look different, but they are actually the same graph, right? If we just rename the vertices and we just move the vertices around a little bit, we will eventually get the same graph, right? And this is a hard problem as well. All right, and that's the end of that graph problems lecture. So now we're going to have a quick look at our next topic, all right, which is directed and weighted graphs. So this is a bit of a lighter topic, so not much content here, but we already introduced directed and weighted graphs from earlier. Right, so so a directed graph is a graph where edges have a direction, right? And a weighted graph is a graph where each edge has a weight, right? Or a cost. Right, why do we need them? That's because in real-world scenarios, the edges are often directional and they often have a sense of cost, right? So we need to consider these kinds of graphs. All right, so formally, what is a directed graph? Right, so directed graph is a graph that has directional edges, directed edges. That means if there's an edge from V to W, right, that doesn't necessarily mean there is an edge from W to V. Right, so a couple of examples of this would be follows on Twitter, right? So if A follows B, that doesn't mean that B follows A, right? It's a one-directional thing. One-way streets, so in the real world you have one-way roads, so those would be represented by a directed edge. All right, now, yeah, so I've already mentioned this. So in a directed graph, edges have direction, and also self-loops are allowed, right? So a vertex can have an edge to itself. Right, so each edge has a source and a destination. Okay, so here's an example of a directed graph. Right, so you see that some vertices have self-loops, and some pairs of vertices have edges to each other, right, but for some pairs of vertices, there's only an edge in one direction. All right, so here are some applications of directed graphs. Right, so the internet is basically a giant directed graph, right, because our vertices would represent web pages, and our edges would represent links, right? So if a web page has a link to another web page, then we say that there's an edge from that first page to the second page. Right, another scenario is chess. Right, so each possible board state of a chess game can be a vertex, right? And there would be an edge between two board states if there is a move, a legal move that takes you from one board state to another. All right, another possible scenario is scheduling. Right, so if you have a bunch of tasks and you want to order them, right? So it might be the case that some tasks depend on other tasks, right? Which means that you have to complete task A before task B, for example. So if you have to do task A before task B, then you can add an edge from A to B, right? Okay, and another scenario is programs. Right, so in a program, you have functions and you have function calls. Right, so your vertices would represent your functions, your edges would represent your function calls. Right, and checking for a cycle in this graph would basically be checking if there's any recursion going on. Right. All right. There's also another example here, journals. So your vertices would represent articles, journal articles, and your edges would be citations, right? So if one article cites another article, then there's a directed edge from the first to the second. All right, so there is some extra terminology that we use for directed graphs. Right, so first of all, with undirected graphs, we have the term degree, right, which is just how many edges are incident on a particular vertex. Right? Also, like how many neighbors each vertex has. Right, with digraphs, because we have edges going in and out of a vertex, we have the notion of in degree and out degree. Right, so an in degree is the number of edges leading into a vertex, so the number of incoming edges, and out degree is the number of outgoing edges. All right. So, we have also the notion of directed paths and directed cycles. So, a directed path is just a path. It's basically the same as the notion of a path in an undirected graph, right? It's a sequence of vertices where each vertex has an outgoing edge to the next vertex. All right, and a directed cycle is just a directed path where the first and last vertices are the same. All right, and we have some other terms. So reachability. So the idea of reachability should be fairly intuitive, right? So W is reachable from V if there's a path from V to W. Right? That's basically it. Now, there's also the idea of strongly connected. Right, so in an undirected graph, right, if V has a path to W, then we say that V and W are connected, right? But in a directed graph, you might have a path from V to W, but you might not have a path from W back to V, right? So we have the idea of strongly connected. So if V and W are strongly connected, then that means there's a path from V to W, and there's also a path from W to V. All right, so a few more terms. These are the last two. So a graph is strongly connected, right, if every vertex is reachable from every other vertex. Right? And strongly connected component is a maximally strongly connected subgraph. Okay. All right, so now, how do we represent directed graphs? We can represent them using the same representations as undirected graphs. Right, so with an adjacency, so we can use adjacency matrix. So if we use this representation, then the matrix isn't necessarily symmetric, right? For an undirected graph, the matrix is symmetric about the diagonal, right? That's because if there's an edge from I to J, then there is an edge from J to I. That's not necessarily true for a directed graph. Right? And in the real world, directed graphs tend to be quite sparse. Right? Just think of these applications here. Right? The internet is very sparse, right? Because each page has very few links. Right? Chess, there are lots and lots of different chess or possible board states, right? But from each position or each board state, there are very relatively few board states you can get to, right? By doing one move. All right. So yeah, so this is what the adjacency matrix would look like for this graph. Adjacency lists. So here is what the adjacency list representation would look like for this graph. So when the graph is undirected, right, if there's an edge between V and W, then that means W is in V's list and V is in W's list, right? But since this is a directed graph, that's not necessarily the case. So for example, let's take this edge from 0 to 3, right? So since there's an edge from 0 to 3, that means 3 is going to be in 0's adjacency list, but 0 is not in 3's adjacency list, right? Because there's no edge from 3 back to 0. All right, so here's the adjacency matrix representation again. Right, and you can also implement your directed graph using an edge list, right? But remember that if you implement your graph using an array of edges, the order of the vertices in your edge struct encodes the direction of the edge, right? So if you put 0 first and then 1, that means there's an edge from 0 to 1, right? All right, so what would be the time complexities? They would pretty much be the same as for an undirected graph, right? So adjacency matrix, so the storage would be V squared, the storage for an adjacency list would be v plus e, right? And the storage for array of edges would be e, right? For an adjacency matrix, remember that checking if there's an edge or adding an edge is O1, because you just check the cell of the matrix. To check the degrees, or particularly the out degree of a vertex, you have to loop through a row of the matrix, right? So that would be O of V. For an adjacency list, adding an edge and checking if there is an edge is O of this expression here, dv, right? So this dv here means the degree of the vertex, right, that you're given, right? And the reason we write this instead of O of V is because graphs tend to be sparse in the real world, right? So even though in the worst case, the degree of a particular vertex could be v minus 1, where v is the total number of vertices, in the real world, that's not really the case. So we write dv here, just to indicate that. All right. For the array of edges, all of these time complexities are O of E, because you have to loop through the array of edges, right? To find an edge, to see if it already exists when you're adding, and to check if an edge exists. All right, so adjacency list is the better representation out of all of these in real-world applications. All right, so here are some problems that we might want to solve on directed graphs. Right, so is there a path from S to T? So this is called transitive closure for a directed graph. So we will get into this next time. So we're not actually going through these problems now. So we're just introducing them here. So what is the shortest path? So for this, you can use BFS. Right? So are all the vertices mutually reachable? So this is checking whether the graph is strongly connected. Right, and here are some applications of directed graphs. Right, so if you have a bunch of tasks, where some tasks need to be completed before other tasks, how do I organize them? Right? How do I decide on an order to do these tasks? Right, so that's called a topological sort. All right, and another application is how do I crawl the web, right? Because the internet is a directed graph, right? So how do I create a web crawler, right? And that can be done using a graph traversal. And here, so we have an algorithm called PageRank, and this is an algorithm that can be used to determine which pages are important. All right, so here is a very special kind of directed graph, which is used in lots of applications. Right, it's called a directed acyclic graph. Right, and it's a directed graph which doesn't have any cycles. Right, that's it. Right, so it kind of looks like a tree, except it isn't, because so you might have two vertices that both have edges to the same vertex, so it's not a tree. Right, but it is a graph. It's a special kind of graph. Right, and this part isn't examinable, but the most common application of a directed acyclic graph is topological sorting, right? So here's the application. So if you have a set of tasks where you need to complete some tasks before others, right? How do you decide on an order to do them? You would decide on that by using a topological sort, right? Don't worry about this. So yeah, another example of where a topological sort is useful is make, right? When you compile, right, the make file lists all the dependencies, right, of each target, right? So the dependencies in the make file actually form a directed acyclic graph, right? It's acyclic because you can't have targets that depend on each other, right? Otherwise, you wouldn't know what to compile first, right? And make essentially uses a topological sort, right, to decide what to compile first. All right. Yeah, and that was just a little bit on DAGs. Don't worry about that. But okay, so how do we traverse a directed graph? Right, we traverse them in just the same way as an undirected graph. Right, so you can just use DFS and BFS that we talked about on Monday, and it should all just work. All right, now just a little bit on weighted graphs. All right, so why do we have weighted graphs? Well, some applications, they require us to consider a cost or weight. Right, so for example, roads, they have a length. Right, so if you represent a road network using a graph, then your edges would be weighted. Right, so each edge STW has a weight W, right? So we have a weight associated with an edge. So here is a weighted graph, right, which is undirected. You can also have a directed weighted graph. All right, here's an example of a weighted graph. Right, so here are the major airline routes in Australia. Right, so the weights here would be the amount of time it takes, right, to fly between two cities. Right, but you could instead have the cost, right, of flying between two cities. Right, that could be your weights as well. All right, so how can we represent a weighted graph? So we can again use the same representations as for undirected graphs, right? With adjacency matrix, with the undirected graphs, we store just true or false, right? But in a weighted graph, instead, we store the weight of the edge, right, in the cell instead of false, instead of true. Okay, and just a slight implementation detail. So you need to make sure to have, so there needs to be a value that represents no edge, right? And in cases where you know that the edge weights are going to be positive, right, then you can use 0, right? But in some cases, maybe you actually do have edges with weight 0, then you need to be careful, right, and choose a value that can't be an edge weight. All right, adjacency list. So it's really simple to represent a weighted graph using an adjacency list. All you need to do is to just add the weights to the node, right, to the list node. Right, I'll show you diagrams of this in a second. Now, also array of edges. So all you need to do there is to just add the weights to each edge struct. Okay. So here it is the matrix representation. Right, so for a weighted graph, so notice that each cell contains the weight of the edge, right, instead of a 1. Right? And for the cells where there are no edge, where there is no edge, you would choose some value which can't be an edge weight. Right? For example, here you might choose 0 because you know that all the weights have to be positive. All right, so here is a weighted directed graph. Right, so here notice that the graph is not symmetric. The matrix is not symmetric because it's a directed graph, and also each cell contains the weight of the edge. All right, here's the adjacency list implementation. So instead of each list node containing just the vertex number, it also contains the weight of the edge, right? So for example, 1 has an edge to 2 with weight 0.6, right? So in 1's adjacency list, we have 2, but attached to 2 is also the weight 0.6. Okay. Right, so fairly simple. Also array of edges. Right, so each each edge struct contains not just the endpoints of the edge, so the endpoint vertices, but also the weight of the edge. Okay. So here it's drawn out as a linked list, but you can also have an array of edges. All right, and with weighted edges, right, that naturally brings up problems such as, what is the path that costs the cheapest, right? So I want to find a path from 0 to 5 with the minimum total weight, right? So we could have problems like that. We also have problems like, how do I connect the graph together? So given a graph, how do I select edges in order to connect the graph in the cheapest way possible? Right, so now we have problems related to cost, and we'll have a look at solutions to these problems in week 7. All right, so that is the content for this sort of mini topic, and I'll see you in week 7, where we'll talk about algorithms for weighted graphs. All right, so see you then, and enjoy your flex week.